So welcome to CS446. Okay, so most of you, I think, were here last time, so you know everything. I'm going to repeat a few of the administrative things that you need to know. And basically, we talked a little bit last time about examples of what machine learning is. I said something about what you need to know. I already said that homework 0 is on the web. Hopefully, many of you have looked at it already, so you have a better idea of what we think you know. Note that homework 1 will be made available next week, a week from today. Homework 0 is just for your pleasure. Homework 1 you'll have to submit. In fact, on Monday, if everything works out, we'll give you a quiz. It's going to be a short quiz. Will not take more than 10 minutes of your time. We're going to do this hopefully once a week. And the idea in this case is going to be to make sure that you have looked and tried to work on homework 0. Okay, so I talked also about the fact that I want you to talk, and I'll give you opportunities today, and talked about a few of the policies. I'm not going to talk about everything today unless there are any questions. Any questions? Okay, so everything is going to be on the web page. All this information is already on the info page. If it's not there and you have questions, please let us know. But we're going to try to keep the web page up to date, and we're going to supply information also on Piazza. Here is information about the team. We have 5 TAs that are sitting somewhere there. Okay. And they're going to have office hours starting from next week and discussion sessions from next week, either next week or 2 weeks. The week after next, okay. The times are going to change slightly, but basically that's it, and you'll see the information. Okay, as I said, everything is on the web. 2 important comments are that we are videotaping it twice, and we will need either volunteers or it will be a chore. We haven't decided yet completely. We need people to caption the videos because it's mandatory that the video will be captioned. I'm also looking for people to scribe the class. I got a few volunteers. The more the better. It's not volunteers actually. I'm going to pay big money if you're doing a good job for this. So, okay, announcements. That's important. If you were asleep so far, no classes next week. But and as I said, section will start the week after. But there will be a first quiz next week, and the first homework will be made available next week. So don't go to sleep completely. You'll have to start working. Okay, questions before we start? No questions. So last time I gave you this puzzle, learning puzzle, the badges game, and I talked a little bit about it. Mostly I wanted you to think about it in your spare time. It's really a machine learning puzzle in the sense that this is an example of the key learning protocol that we're going to study this semester, supervised learning. What you got there was a bunch of examples. Names were examples. Some of them were labeled positive examples. Some of them were labeled negative example. This is really something that happened if you read what's written either there or on the web. Everything, by the way, is available also on the web. The example and the story. This is something that happened a little bit more than 20 years ago. A machine learning conference in '94. I was a graduate student, so you can see my name on the list. These are the people that registered to machine learning at that time. It was a small conference, and you could see that I was a positive example. And the people that organized the conference gave a learning puzzle. They basically, on the badge of each person that registered, they put a plus or a minus. You are either a positive example or a negative example. And the challenge for the participants was to figure out what is the hidden function that governs these labels. And that's the question that I asked you. And I know that last time, a few people already told me that they know. Now, I don't want to know the answer yet, but who knows the answer? OK, somewhere over there last time said that they know and gave me a reason for why they think they know. You want to repeat?
Like repeat the same thing I said?
Yeah, what you said last time.
Oh, because the answer was correct for all the examples on the sheet.
OK, so he knows the answer, and his justification for why he is sure this is the right answer is that his answer is consistent with all the examples on the paper I gave. So the first thing I want to ask, are you happy with this justification? So I see some yeses. This is yes. Many of you are happy. Can you give me a better justification? Yeah.
I mean, there could be sort of overfitting, where he's like taken all the cases and he's labeled them correctly, but he does, like, maybe what he has, it won't work on the next example, it'll only work on these.
OK, so that's why you're not happy with this example. So I'm going to say differently what you said. Can you give me this? This is the... So this function, this is a function, right? This piece of paper, it's a function because it maps names to pluses or minuses. This function is also consistent with all the information. And this function is not that informative because it doesn't know whether you are a positive example or not. Now, I bet you know whether he is a positive example or not, but your justification wasn't convincing enough. Do you understand why I'm not convinced by the justification? Because here is a simple function. Just write everything down that is also doing it. So give me a better justification. People that know the answer. Why are you sure that this is the right answer? Why do you think? Why did you stop searching? You thought a little bit about it. You say, oh, wow, it's this. Yeah.
First, because when we first thought of the problem and we tried to get the solution, we did not see everything. We kept, I kept the first row aside and only took these cases, which were on the second and third column, and just found a particular solution and then tested them with the first row. So
okay.
After testing them, I would say that, hey, this works for this first row or first column.
Okay, are you happier with this justification? Why? Yeah?
Because he treated some amount of the data as unseen data that he might not have seen.
And he showed, moreover, that this hypothesis that he has some predictive power. Okay. I'm looking for an even stronger justification. Why are you sure that, or pretty sure, let's say, that your answer is good? Let's try again. Who knows the answer? There were more people yet before. I'm not going to pick on you if that's the worry. Who knows the answer? Let's put it up there, and you look at it again. So this is, let's see if it works. Yeah, it works. So here are some examples. Hopefully you can read it. Oh, in fact, I have it also here. So let's, here are some of the examples. Test your answer on this. Is there a unique answer, you think? So let's go back to the people that volunteered before. Give me a better idea. Why did you stop searching for a better answer?
Me?
Yeah.
Because I couldn't have found, like, if I did find a better answer, I wouldn't be able to know with the given data, right? Because I was already right 100%.
But in what sense your answer was good? Okay, let me give you another hint. Let's use this artifact again. Yeah, suggestion?
I don't know the answer, but probably if you know the rule behind this and you're sure that you can classify anyone with that same rule and that it will be right, then that is probably good.
That's good, but so how long is this answer? This is also an answer. How long is it? Like 200 names times 10 characters each, 2,000 characters, plus or minus. How long is your answer?
I don't really answer your question. Like, it's a rule that I guess could be written in there.
How many characters do you need to write it down?
Probably 20, I don't know.
Okay. Yes?
I don't have the solution, but I think it could be that the rule is very simple. So it simplifies. It's much simpler. I think is what you mean. Yeah. So like it's not like very complicated or something like that.
Right. It's a very, very simple rule. Yes?
I use only one vowel. That's it. One letter, so one character. So.
I think that's not enough, but we can check your answer later. Your encoding scheme is too tight, but yes, the answer is very, very short, and that's a convincing thing for you. It's much better than a piece of paper full of characters. And that's a convincing argument, and I bet that was the reason you stopped, even though you didn't articulate this. Okay, so before we get into the answers and so on, here are just two examples. Which problem was easier? I know that you didn't do your homework, and probably this is a good lesson. Next time, please do your homework, because all of you can solve this puzzle. Some of you will solve it in a minute, and some of you will solve it in 10 minutes, but it doesn't matter. I mean, spend some time and think about it, because this is really the core of machine learning from many perspectives. So which problem was easier, the one I gave you, or the one that was given to the people that participated in the conference? Yeah?
The one you gave us because we had all the data.
Okay, one reason you have all the data on one piece of paper, and they had to look around, look at badges of people. Maybe they didn't even see all the data because they couldn't meet all the people. Yes?
Well, it's because we know it's solely dependent on the name.
Right, so that's another reason. I gave you the data, and I told you it's here, and I gave you only the names. People in the conference could think about the fact that it could be the height of the person, or the university they come from, or their shoe size, or something like that. And for you, I restricted the scope of what properties of the name dictate plus or minus. Much, much easier problem. This is something that you always want to have in a learning problem. So, much easier problem. Okay, so this is the story. So let's get an answer. Who wants to give me the answer? Okay, you were first.
If the second letter is a vowel, that doesn't include Y. Y is not a vowel.
Second letter of?
The second letter of the first name.
Second letter of the first name is a vowel that makes this a positive example. Otherwise, it's a negative example. Okay. So what is a vowel? Did you understand the definition of the function? What is a vowel? Here.
It's a set of letters, A, E, I, O, U.
But it's not part of the input. I gave you just a bunch of characters and a plus or minus. I didn't say vowel, not vowel. It's not part of the input. So this is what? Where did you get vowel from? All of you agreed on this, it seems. All of you know what vowel is. So vowel is a set of 5 characters. If instead of vowel, I would say the second letter of the first name is one of X, Y, Z, C, K. Would that be as easy a concept? Yes, no? Who says yes? Who says no? Why not? Yeah?
Because you already have an association of the vowels together right now.
So for you, it's not as simple because you have this notion of a vowel, and because you can write this function using vowel, it's a very simple definition for you. You buy it. If it was a longer definition, maybe you wouldn't buy it. You look for something more compact. What about your program that you write? Is this the same for the program or not? Think about writing a program for this, right? Which is another question I asked you last time. I don't know if you thought about how to write a program that will figure it out. But let's imagine that you know how to write a program. Is it as difficult for the program whether it's a vowel in the second place of the first name or one of X, Y, Z, C, K? What do you think? Yeah?
I think it's the same, but that's what I've been is like a certain set is different and stuff on the spot.
So what does a program like this need to do? How would it work? Imagine that you want to write a program that learns this function. What would you do? Anyone thought about it? Yeah?
Take each character as input and then adjust the weights of the inputs, the corresponding positive and negative function.
So for each character in the input, you will decide whether it appears in positive examples or negative examples. Okay, that makes some assumptions, right? What assumption have you made in suggesting that this is the program? Yeah.
That the position doesn't matter of the letter.
That only the characters matters and the position do not matter. And in fact, we know that this is not true already. More assumptions you've made, yeah?
It's not based on length, and it's actually based on characters.
Right, so maybe it's just based on length of the first token, the second token, the sum of the tokens. Could be other things, right? So we need to improve this program. Any suggestions? But that's actually a good start, right? So basically what you've done is you said, I'm going to hypothesize some properties of the names. For example, does it have A, does it have B, does it have C? Maybe I'm going to incorporate positions. Does it have A in the first place, the second place, the third place? Does it have C in the first, and so on? And eventually I'm going to start searching and find something, perhaps. Any other suggestions of how to go about doing it? Okay, so this will be your second problem set. By that time, you will know how to do it. So let's see. So we talked a little bit about whether your hypothesis has a prediction power or not. So if it's just the list, the piece of paper here, it's correct. But it doesn't give me anything. It doesn't have any predictive power, and you want a function really. We talked a little bit about the representation. You realize that the people in the conference had a much larger set of potential representations to choose from than you guys had. And even for you, it's not completely clear what are the components of this representation. Are they going to be the characters? Are they going to be the character and positions? Is it going to be the length? Is it going to be maybe the position in the list? I'm not sure what could be there. But the representation is crucial because if you don't choose the key components, you'll never be able to do it. Another important thing is this issue of the vowel here, right? So for you, the fact that the second character was a vowel was actually a key simplifying assumption. You have to think about whether this is true for the program that you will write, and to what extent, if you tell the program the concept of a vowel, will it simplify its learning or not? What do you think? Let's assume your program also knows what a vowel is. Does it matter? We'll take a vote again. Who thinks it's going to matter? You can use it. How would you use it? Yeah?
I mean, then it becomes more of a binary thing where it just maps whether vowel or not, rather than 26 things that it has.
If you know that the concept of a vowel exists and it's there, it puts together potentially a lot of things that otherwise you'll have to search. Maybe you'll have to search all subsets of some size, whether an element of this subset is in the second place or the third place or the fourth place. If I give you some interesting subsets that have some unique properties, maybe you'll only search for them. So there's a lot of things that have to do with it. But this also means that some of the learning that you did in order to figure out this function did not happen once or after I gave you this piece of paper. Some of it happened before, where you decided that some concept or sub-concept could be important. Vowel is something important. You learned that years ago. And so there's a lot of issues here, even though we did not get to any algorithm yet. I don't know how you did it, and you don't know of what algorithms could allow us to do it. In fact, a lot of algorithms will do it, and we'll see that a little bit later. Okay, so I'm putting this again, the kind of the spam example that I gave last time, just to remind you that even there, in exactly the same way, had I told you some aspects of this email message that are important and some that are unimportant to determine whether it's a spam or not, this will simplify your problem a lot. It's kind of like telling you that it's all in the name rather than in many other issues. So this is kind of focusing on the right part of the input is a big step first. Okay, so any questions on this? Okay, so the game that we've played here is the game of supervised learning, which is the key protocol, the key learning protocol that we're going to talk about. So we really care about systems that apply function f to input items x, in this case strings of characters, and return some output y, which is f of x. So we're going to have some input, we're going to have some output, and we're going to ask the question of what y can be there. What f of x could be there. So a supervised machine learning algorithm or supervised machine learning deals with the systems where f of x is learned from examples. You give me a bunch of x's and y's, and I want to infer this f. So why do we need this learning? The key reason is because we want to apply it when we don't know what f is. There is a lot of data there, and potentially there is a simple rule, simple under some definition, that actually dictates or governs how the labels are being set, but we don't know how to write it. It could actually be simple. In this case, you would agree that the rule is simple, but without looking at a lot of data, and coming up with clever ideas, you won't be able to figure it out. And you won't know ahead of time how to write a function that predicts whether any of you is a positive or negative example in this game. So this is where we want to use learning. So again, this is the game. We start with X, space of X's, capital X, and we call this an instant space. The space of possible Y's, in this case, a binary space, plus or minus, 0 or 1, is the label space. And we assume, for simplicity, that there exists some function that governs the labeling of the data. Our goal is to find a function g that is identical to f, or perhaps as close as possible to f. So the game we are playing is, there is some learning algorithm that takes training data in the form of pairs x and y's. X, again, is the name, y is the positive or negative, and eventually learns a function or a model, right? So learning examples come from some distribution that we're going to call it the training distribution, and eventually the learner returns this model. So this is an important learning protocol. Can you think about other learning protocols? Just to make sure that you understand the game here. Yes?
Some instances you don't have the labels and some don't have.
Okay, so sometimes I only get X's, but I don't get the Y's next to them. That's an example of a learning protocol. What was the learning protocol used by the people in the conference? Yes?
Sometimes you can manually give some data or definition to the learning algorithm so you can find that correlation quickly.
Okay, so you can give maybe some hints to the learning algorithm. So that's actually sometimes a good idea. I don't know how to write it down here. What was the learning algorithm used by the people in the conference?
They were given x, y pairs one at a time.
One at a time. So basically they were given one x, y. They thought about it. Then they went to see another person, another x, y, and so on. So it was more kind of in an online fashion was given to them. You could even imagine them doing the following thing. They would actually look at one example, form some hypotheses, then go to the second person, evaluate their hypothesis on this guy, and see whether it's correct or not. If it's correct, they'll be happy, maybe continue to other people. If it's incorrect, they'll change it, given this example, and keep on going. Right? So it's, again, it's an online fashion, but another learning algorithm. One other protocol. Yeah?
So some of the Y could be intentionally corrupted by an adversary.
So there could be error, could be noise. The noise could be in the Y's, as you suggested. So some of the labels were wrong. The noise could also be in the X. Some of the X's are wrong. And that always happened. When you sent me email after the lecture last time, some percentage of the email that you sent was wrong. So I asked to send a specific string. X% of you did not send this string. So there's always noise in the input. So that's a good thing to know about. And that reminds me that I should say something about registration. I'm sure you all. So there is a waiting list. It's a long waiting list. Some of you already got in from the waiting list. And my assumption is that by the end of today or tomorrow, at least 20 more will get in. I'm not so optimistic as I was on Tuesday morning that all the waiting list will get in because it's long. But I believe a large fraction of it will get in. So just that you'll know. But as I said, there is a long time. There's a few weeks by which you don't have to really be stressed about it now. What I do request again is that if you decided that you're not going to take the class, please leave the class as soon as you can. If you want to drop off the mailing list, same thing. Let me know as soon as you can that you don't want to be on the waiting list. Okay, and let's continue then. So we talked a little bit about how we train. Then we have to test. We have a hypothesis, we want to test it. So we typically are going to reserve some label data for testing. So this is label data that no one saw before. We're going to show the raw test data, only the access to the learning algorithm, look at the Y labels that are true and compare them to what the algorithm predicts, the G of X's. So this could be one way to test it. If G of X1 is equal to Y1, we're happy. Otherwise, we're not happy, and we're going to count mistakes. Can you imagine other ways to evaluate? So the way I suggest, yeah.
We can have more X's and verify that works at all X inputs.
Say it again, I didn't get it.
We can have more X values and verify that it has a solution for all the inputs and doesn't fail off some of the inputs.
That you can evaluate G on all the X's. Yeah. Okay, I'm assuming here that the G has can run on all the domain, and X's come just from this domain. So I can always evaluate G. But how do I know whether it's good or not? Or how do I judge myself whether it's good or not? You can do in multiple ways. You can just count how many times G of Xi is Yi, or
you can sort of define a notion of distance, then you can see how far you are.
If I have some notion of a distance, let's say it's not just Boolean 0, 1, but rather it's a real number from 0 to 1, maybe I can measure error. How far is G of X from Y? And there could be some other ways of doing it. So just correctness is not necessarily the only way. We're going to see other ways. Okay, so hopefully with this example, some things are clear. This is just going back to what I showed last time, what we're going to do in this class. I'm not going to dwell on it now. We're going to start talking about algorithms. And in fact, I'm going to hopefully start talking about algorithms today and give the first real example of learning. So I want to start with terminology, though. So what is the game that we are playing here? We're giving a set of examples, X with a label, which is f of x, for some unknown function. We want to find a good approximation of the function f. Maybe identical to f, maybe just a good approximation. We'll have to define that. So x gives us some representation of the input, and this is an important process here. So the process of taking the input element, could be an image, could be a sentence, could be a document, could be just a string, a name, and mapping it to an input that the learning algorithm can take is itself a key step in the machine learning process. We call it a feature extraction process. It's hard, both computationally and conceptually. In fact, if you think about the lifetime of a machine learning algorithm, you will realize once you start using it that most of the time, both CPU time and your brain time is being spent on the feature extraction process, not on the learning itself. Moreover, it's ill understood in the sense that we don't have good theories for this, but very important. So this x, once we represent it, the input, we can represent it as a Boolean vector, 0, 1 to the n, real valued vector, and so on. And then the second component is the target function. And this could be binary classification, could be multi-class classification, multiple values. I want to know what's the topic of this document. Is it news, finance, sports, and so on? Or it could be just a real valued number. And a lot of examples that you can think of, and I'm listing a few here, can be written or can be reduced into this multi-class classification problem. Here is an input classified into one of k values. Even when the problem seems a lot more complicated, you can reduce it to this. And I'm not going to spend more time on examples. So I want to start by mentioning at least some of the key issues in machine learning. So this is perhaps the most important slide, not only today, in the class, because it really gives you the process. And while you always think about the last component in this process, really, the process has 3 steps. The first one is modeling. How do we take an application and formulate it as a machine learning problem? How do we represent the data? What learning protocols are available to us and what makes sense in this scenario? Representation. I mean, what function should we use as candidates for our learning task here? Not every function can do it. And this decision is going to have a lot of significance in whether we are successful or not. How do we map the data, the raw data, into our X space, our instance space? And the question, of course, is there any general approach? Can we say something rigorously about these things? And finally, algorithms. So, of course, we're going to spend a lot of our time studying algorithm and analyzing algorithm. But the important thing from our perspective is going to be, how do we know whether one algorithm is better than the other? Can we say something about algorithms? How do we define success? I already hinted about it a few slides ago. So it's not necessarily that there's one metric by which you decide whether you've done well or not. There could be multiple things. As we said earlier today and last time, the key thing about learning is not how well it's doing on this data that I see here in this piece of paper that I gave you, but rather how well it's going to do on data that you've never seen before. Can we generalize for it? So the issue of generalization ability versus overfitting is going to be crucially important. And of course, the computational problem is going to be an issue. As computer scientists, we want to know, can we compute this efficiently? Is the learning problem tractable or intractable? And we'll be able to say things about all these things in the course of this class. So I'm asking these questions in a little bit more specific or with the right terminology. What is the instance space? What is X? What kind of features are we going to use? What is our label space? What kind of learning task is it? Is it going to be mapping things into a binary thing, into a categorical things, into a tree? Are we going to choose tree as our labels? What is our hypothesis space? What kind of functions are we going to learn? Are there some function spaces that are easier or harder? Are there function spaces that are smaller or larger? All these things will have a lot of impact on our ability to learn, and we'll be able to quantify these things as we go. What learning algorithms are good? And of course, what is our loss function or evaluation metrics? How do we judge whether we are successful or not? So all these things are things that we're going to learn from the instance space, mapping X to Y. This is really a crucial step, and I want to give an example of what could this be. So the first thing we want to be able to do is we have to define features on our input. For example, when we looked at email messages, does this email contain the word money? Yes or no? This could be a feature. Does it contain another word? Yes or no? Numerical features. How often do you see money in this email? What's the width or height of this bounding box in an image? In the example that we've seen before, what is the length of the first name? Perhaps that's a property that we want to highlight. So in the badges game, I asked you for ideas for what kind of feature this would be. You gave me a few. Here are a few more. And you can try to think about how do I encode this, right? So I want to be able to take this x and encode it as a vector of properties. So eventually I'm going to get some feature vector that I'm going to place in a vector space. In this case, two-dimensional vector space, because I don't know how to draw it in more dimensions. Here is an example of this encoding. So for example, I'm going to take names from the learning puzzle that we talked about before, and I'm going to encode them by the characters. So I'm going to define one big vector. It's going to be split into groups, and each group will represent the character. Either I'm sitting on the first character, the second character, the third character, up to m characters. Within each group, I'm going to have 26 times 2 plus 1 position. Why do I want 26 times 2? What will I encode? I'm going to encode the character and its case. So, for example, the first group here is going to be representing the first character, and this means that it's capital A. The second group represents the same character, and it represents a B. This one represents the third character, it represents an E, maybe, and so on. And I will also want this plus 1 because maybe I want to say there's nothing here. So the number of group is going to be the upper bound on the length of the name. This is one way to encode some of the features. Now, I did not encode length features. I did not encode many other things that you could imagine to encode here, but this is just one example. And you'll have to do this work of encoding the input somehow when you think about a machine learning problem. As I said, and I'm going to say it probably a few more times, the choice of feature is really crucial to how well the task can be learned. But there is very little we can say about it. We will try to think a little bit about some general principles, but at the end, these are application specific. The second component is the label space. And as I said, we can talk about multiple label spaces. You can think about binary, you can think about multi-class, you can think about structures. But we are going to talk for most of the class, mostly about binary classification and make the case that everything can be reduced to this. So this is going to carry us a long way. I want you just to realize that there are other options. You can think about regressions, you can think about ranking, you can think about structures. And at the end, it's the model. So what functions are we going to learn? And let's start with the relearning problem then, now that we have the terminology. So here is a learning problem. It's a learning problem with 4 inputs. I already abstracted the application away. I encoded everything as 4 binary features, x1 up to x4. I give them as input to this box that hides this unknown function, and it returns y, f of x. So what I've given you here are 7 examples, right? So the label of 0, 0, 1, 0 is 0. The label of 0, 1, 0, 0 is 0, and so on. What function is it? Suggestions? Yeah.
X4 and not X2.
X4 and not X2. Here's a suggestion. Is this correct? Let's check. If X4 is 1 and X2 is off, it's a positive example. Otherwise, this is another positive example. Also, X4 is 1, X2 is not. And all the rest are 0. So, that's the function. Is that the function? Who says yes? Wake up.
Not necessarily.
Okay, so you have another suggestion.
X1, X4, or X3, X4.
Okay, so X1 and X4.
Or X3 and X4.
Okay. That's also true. Is it the same function? In what sense it's not the same function? Yeah?
You can have just like one for x4 and zeros for everything else. And in that case, that would be classified as 1. The other example would be classified as 0.
Right. So I want to say what you said in a more general way. These are not the same function, even though they agree on these 7 examples. But they are not the same function in the sense that there exists at least one instance, x1, x2, x3, x4, on which they differ. So which one should I use? This one or this one? So what is the problem we're having here? Right? So we already have, in a minute, 2 possible outcome of your learning algorithm, whatever learning algorithm you use. So here is the whole picture here, right? So on 4 inputs, I can have 16 instances. I just listed all the 16 instances. Everyone agrees that I can have 16 instances, right? How many functions are there on 4 inputs? Yeah?
Is it 2 to the 2 to the 4?
2 to the 2 to the 4, 2 to the 16, right? So there are 2 to the 16 possible function. Why is that? So against each one of these instances, each one of these 16 instances here, I can either put 0 or 1. 2 options against each one of those, right? So it's 2 times 2 times 2 times 2, 2 to the 16 is the number of functions. If I change one of these labels, I got a different function, right? Because at least on this point, the functions disagree. So I have a lot of functions, 65,000 functions. So you gave me one, you gave me one. How many functions are actually possible here, given this learning problem? Just a little bit less, right? Because I already gave you a few of the examples, right? So I told you these 7 examples, this example must be 0. This example must be 1. This must be 0, and so on. I left only 9 examples open. So how many functions? 2 to the 9, still a large number of functions. And you gave me 2. So how do I know what to do here? So the first question you should ask yourself, is learning even possible, right? I gave you a few examples. There's so many options here. Yeah?
Collect more data.
Collect, how much data do you want?
All of it.
All of it. Okay, so if you do all of it, then the table is the function. But, and true, that's going to be the only function. But that's not a realistic and not an interesting situation. So if instead of 4 bits, there will be 100 bits, or 1,000 bits, or 1,000,000 bits, you see that you will never see all the data. And the number of functions is going to grow doubly exponentially with this. So is learning possible?
So in this case, any of the 2.9 would be possible and would qualify as a good answer. But in a more realistic case where x1, x2, x3, x4 are real features, like x1 could be the height of someone, x2 could be his weight, then maybe we could assign hints, and maybe x2 and x4 might not be compatible together. So maybe you'd say that x4 and not x2 isn't a very good hypothesis.
Okay, excellent. So the only solution here to this answer is this notion of hypothesis space. We have to make assumptions. Without any assumptions, no, it's not possible, because there are just too many options, and we don't have any way to prefer one over the other. So we have to make restrictions on the hypothesis space. We're going to assume a set of functions, capital H is going to be a set of functions, and say, I assume that the function that you're after can be expressed this way. It comes from this family of functions. Now learn. Example. Let's assume that I'm assuming here that the target function is a simple rule. It's x1, xi, and xj, and xk. That's it. This is how I'm going to express my function. Now, if you think a little bit about it, this restricts the space to only 16 different functions. And now I can check for each one of these functions, and I've listed the 16 functions here, whether they're consistent with my data or not. And my plan is, if I'll find a function that is consistent and it's in my hypothesis space, I'm going to be happy and say that's the function. Now, if you check these examples, none of these functions actually is consistent with the data. You'll have to check it yourself. What I've done here is I've written the function, and here I've written the counter example. Why this isn't the right one. For example, if you look at x1 and x2 and x3, this is not the function because on 0, 0, 1, 1, this function says it should be a negative example, but in the example, this is actually a positive example. So that's not a good one. And none of them is. Not a good hypothesis space. We can try another one. For example, I can try something that I call here m out of n rules. The definition here is that when I say 2 out of 3, what I mean is out of these variables, for example, let's take these 3 variables, if 2 of them are on, the function is on. Otherwise, the function is off. Okay, it's another class of functions. And again, I went over these functions, and surprise, I got this one. So this is the only function that is consistent with the data in this family of m out of n. And if you check, you'll see if 2 out of x1, x3, x4 are on, everything holds. Notice that this is different than your function, and it's different than your function. But it's consistent, and it's in my family, so I'm happy with it, and I'm saying that this is my target function. Okay? So the key thing to learn here, and this is really crucial to understand, even though a lot of people that do machine learning today haven't thought about it yet, it's really crucial. We are going to make assumption. It's important for you to understand this. We're going to go back to this a lot in this class to highlight where these things are coming into play. Important. Okay, so we found a consistent hypothesis. I do want to say something for people that were expecting that this is going to be what you read in the newspaper. It's a neural network class. Yes, this function is actually a neural network. You can write it down as a neural network, and we'll actually see why it is a neural network if you care about it. So don't be disappointed by the fact that I'm talking about Boolean functions. This is a special case, and a pretty important case at that, of other representations that are in the news. Okay, but the key thing that I said so far is that I presented learning as a removal of remaining uncertainty. We are making assumptions. If we knew that the unknown function was an m out of n Boolean function, then we could do it. We use the training data to nail down which function in this collection is the right one. But, of course, that means that learning requires guessing a good hypothesis space. And in fact, we are doing it all the time, directly or indirectly. Sometimes we can start with a very small class and enlarge it until it contains the hypothesis that fits the data. But it's important to realize that we could be wrong. We may make assumptions that are wrong, and then we'll have to be able to think about it and do something else. Okay, so we already discussed the fact that there could be other possibilities. I think this is your function. But as we said, there are 2 to the 9 functions, so all of you can come up with your own individual functions, and there'll be a few to spare. Okay, so any questions on this? That actually gives some general strategies for machine learning. Just this simple observation, it says something about how do we think about, or how should we think about machine learning. We could either think about flexible hypothesis spaces. very, very general hypothesis spaces that can express everything. Decision trees is one. Neural networks, if they are large enough, could be enough. Or we can think about nested collections of family of functions. And this has some advantages, and as we will see, some disadvantages. Or we can develop some special representation languages for restricted class of functions, and we'll see that that's often a good strategy to use. In either case, we want to develop algorithms that will find the right hypothesis. What we did so far in this simple example, we just tried all options. That's not going to scale to interesting cases. And then hope that what we've nailed down as our target function is going to generalize well. Of course, rather than hope, we're going to do a little bit more. We'll try to develop some theories that will give us guarantees of when things will generalize well. Okay, so I want to finish this class today in the last 15 minutes with a more concrete example that will lead us to an algorithm. Let's see if we get to an algorithm. And my example is going to be one of the examples that I started with last week. It's a context-sensitive spelling example. I don't know whether to laugh or cry, and I want my learning algorithm to predict which kind of weather, WH or WE, is the right type of weather here, right? Binary learning problem. First of all, how do we make this a learning problem, right? So we are in the modeling step here. What do I have to do? There was a suggestion here. Yeah?
Specify the instance space and the label space.
Right, so I have to encode this. So the label space I specified. I told you it's weather, weather. The instance space I have to specify. So I have to encode this problem, right? So here is the problem. I'm going to look for a function, f, from the space of all sentences to whether or whether, binary classification. And we need to define the domain. Suggestions. How do I define this domain? You all understand what I'm saying when let's define the domain. Yeah?
Examples from web articles.
Okay, I have a lot of sentences. I took all of Wikipedia. That's my input. But I still need to define the domain, right? So okay, word-based representations you're suggesting. Let's make it a little bit more concrete. Here is what I'm going to do. For each word in English, I'm going to define a Boolean feature. Boolean, 0, 1. XW is going to be 1 if and only if W is in the sentence. Otherwise, it's 0. Okay? So these are my features. Okay? That's kind of what you had in mind. That's it. So this way, let's assume there are 50,000 words in English. So I'm writing a vector of size 50,000. And for each word, let's say the word I is the 17th word in the sentence, in this representation, the 50,000 dimension. So in this sentence, I is going to be 1. In other sentence, I is going to be 0. The 17th place is going to be 0. So that's my encoding, right? So I encoded every sentence. I have a method to encode every sentence as a bit vector, if you want, of dimensionality 50,000. Okay? That's clear? So now I'm working in the space 0, 1 to the 50,000. Some points are whether WH points, and some points are WE points. Okay? So the picture is kind of like this. Okay? That's the picture. I have a space. It's not two-dimensional as you think here. It's 50,000 dimensional. And it has some red points and some purple points. That's the learning problem. Okay? I did not talk about learning protocol here. But we can talk about learning protocol for a second. So what is the learning protocol? Do you want to think about it as a supervised learning algorithm? Where are you going to get the labels from? Where? The sentences. Okay, so that's actually the interesting thing. This is why I actually asked this question. So I'm going to use a supervised learning algorithm here because we don't know better. That's what we know how to do. You'll see it later on. We only know how to do supervised learning. What we do know is sometimes to trick ourselves into supervised learning algorithm. And this is what we're going to do here today. I'm going to take all of Wikipedia, for example, as my data. And I'm going to make the assumption that is largely correct, that Wikipedia does not have spelling mistakes. So when I see a sentence with whether WH, it's correctly used. I'm going to drop it from there and take this as a sentence which is positive for whether WH and negative for whether WE. I'm going to see another sentence that was used whether WE, take it away, present it to my algorithm as an example that is positive for WE, negative for WH. So I have a supervised scenario even though no one labeled the data for me. I just made an assumption and used this as my labeling algorithm, if you want. And that's an important trick that in somewhat more sophisticated way is crucial to today's machine learning because we can never hire enough people to label data. But with this simple trick, now what I have is a supervised learning scenario, and we can continue. Okay? So we place these points here, and now the goal is to find a function that separates the data best. Right? Clear? So here is a function that separates the data. Here is another function that kind of separates the data. Another function. Another one. Which one do you want to take of these? You want to take the blue line. Other suggestions? The green line. The green curve, let's say. Why do you want the green?
Because they separate different functions successfully with no exception.
So the green separates the red points from the purple points perfectly, while the blue doesn't. Why do you want the blue? So the green might overfit the data. When I give you a new example, who knows where is it going to lie relative to the green? Intuitively, we will have to work a little bit to make this intuition a little bit more rigorous. It will take us a few weeks. But intuitively, you'd say, you know, the blue is much simpler. It's kind of like the vowel rule rather than the list. Right? It's exactly the same case. But the blue gives us an intuition that it will generalize a little bit better. Maybe it makes a couple of mistakes, but it will be okay. The green, you can always separate the data if the data is no noise somehow, but who knows what's going to happen with the next example. You see this intuition here? Hopefully you share this intuition, and as I said, we will actually make this a lot more rigorous. So which function to choose and how to define best is tricky. It's not as simple as you think. So it's really the issue of memorizing versus learning, accuracy on the test, on the training data versus simplicity, how well we do. Right? So even between the lines here, right, there are 3 different lines. You have to distinguish between them. In fact, there are infinitely many lines. I just drew 3. And we have to choose one if we want to choose a line. So all these are issues that will impact, or if we know how to think about them, they'll impact the generalization of your learning algorithm. And of course, there's the question of how to find this algorithm that we'll get to, at least hint in the next 5 minutes, and then do it next time. So one possibility to constrain our problem is to say, you know what? Let's define the learning problem instead of find a function that best separates the data. I'm going to change it to find a linear function that best separates the data. What do I mean by linear here? So by linear, I mean linear in the feature space. So I already defined my feature space. These are the 50,000 Boolean variables. And linear in this space what I mean is the following. If X is my data representation, it's a 50,000 dimensional vector. My line here is also a 50,000 dimensional vector that I denote W. This is really my classifier. And I'm going to say that a function is linear if I can write it as the dot product W transpose X. Okay, so essentially think about it. What is a dot product? Linear combination of the X's. Right? That's a dot product. And I'm going to make my prediction by taking the sign of this. So if this dot product is positive, I'm going to say that Y is positive. If it's negative, I'm going to say that it's negative. So if it's positive, I'm going to say WH weather. And if it's negative, I'm going to say WE weather. Okay, so at least I have a prediction rule. And the question that remains now is how to do it. Now, you can complain here, and you can say, you know what? Why did you choose linear? Most functions are not linear. So it's true. Most functions are not linear, but many functions are linear. In particular, if you think about it a little bit, the functions that we talked about earlier today, for example, the conjunction, these are linear functions. What do I mean again by linear? There is a weight vector. I have here features. The features are x1, x2, x3, x4, x5. And I have weights. I can take a weight vector, dot product it with this vector of x's, and get something that behaves like a conjunction. Do you want a suggestion? Give me a suggestion. Why is this a linear function? So again, a linear function is this. Is a function that I often will drop the transpose from the W because it's hard to carry it, but you'll understand that what we mean is a dot product between a column vector W and this row vector X. And I will have theta perhaps in general, which is a threshold. So I don't care whether Wx is positive or negative. I care whether Wx is larger or smaller than some theta, which can be written here as this linear combination. And the question I'm asking is, why is this a linear function? Can you give me the W and the theta?
So I think W should be like vector 1s. Theta is just like the number of n terms. Oh, sorry. I'm sorry. I think I'm
You're on the right track, though. Yeah?
The weights are just ones and theta is zeros.
Okay. So you're suggesting that all the weights will be 1, but who cares about W2? You want W2 to be 0. You want W4 to be 0, right? Because the conjunction is only of x1 and x3 and x5. So if you take this weight vector, W1 is 1, W3 is 1, W5 is 1, and these two are 0, when you dot product it with any bit vector of 5 dimensions here, it will behave, and theta is 3, the size of this conjunction, this linear function will behave exactly like a conjunction. Right? This is why I said before that you can think about all these things as neural network if you wanted. It's just conceptually an easier, simpler way to think about it. And you can think about many other functions. The other set of functions that we talked about, at least m out of n, I'm not going to go over it now, but you will think about it and convince yourself that this is also a linear function. So many functions are linear, if you don't, even if you don't think about them as kind of linear algebra operations. But many functions are not. For example, XOR is not. This is a function that many of you have seen, x1 and x2, or not x1 and not x2. Geometrically, you can think about XOR this way, right? So on the diagonal, you have positive examples. On the other diagonal, you have negative examples. It's not linear. You cannot separate with one line. Similarly, if you want to think about it in a continuous space, here is my examples are blue points and red points. They have one parameter, x. You cannot separate blue points from red points with a line. What would you do if I tell you we're going to learn only linear functions? One option is to say, sorry, we cannot do it. Yes?
Add another dimensionality.
What does it mean?
So here when we have x, we can add a y-axis, and each dots have their height, and then it's possible to do the line separately.
What will be the y dimension? So that's the information I have. All I have is x. But here is what I'm going to do. I'm going to cheat. I'm going to take, given that I know that this is not working, I'm going to take x squared on the y dimension. So I did not add any information. I knew x squared. But because I'm plotting now the points as x comma x squared, now I can separate with a linear line. So you see that this is an important trick, a representational trick. I did not add more information. I just represented the data differently. And now I can use a linear function. So the reason I did this, and of course I can do this also in the Boolean domain that I showed before with the XOR function. We're going to talk about it also in the discrete domain, but I don't want to do it now. The idea is that representation is crucially important. Sometimes you have the data, but if you don't represent it right, you cannot use it for learning. If you do represent it right, you can represent it. So I'm going to skip this other transformation. And the third step that we're going to start with next time, and reminder, next time is not going to be next week, no classes next week. It's going to be Tuesday in 2 weeks. We're going to take this data and figure out how to learn. Okay, thank you.